The idea here is that one of the limits of string theory is supposed to have a low energy version, which is a supergravity theory on a manifold with boundaries. It was first formulated back in 1995 or so by Harava and Witten, and the theory has certain features which are particular to boundaries as opposed to branes or sources. And what I want to try and bring out is the features that are particularly present when we have boundaries as opposed to branes. Now, it could be that some of these ideas will carry across from boundaries to branes and may introduce some new ideas for branes as well. So I'm going to say something about, the message is boundaries are not the same as sources, not the same as branes. Now I'm going to say, to give two examples, I'm going to look at anomaly cancellation, heterotic M theory, where there seems to be some new terms when you take the boundary seriously, and these terms may be seen perhaps in string theory, heterotic string theory. And then I'm going to say something about moduli stabilization and a mechanism for obtaining a vanishing cosmological constant, which depends very much on the boundary conditions that the theory has. And these are two things that depend very much on having boundaries as opposed to branes. I noticed trolling the internet that back in the 19th century there was a theory of duality. It was actually a theory of insanity. The idea that was that the two halves of your brain, if the two halves of your brain weren't communicating properly with one another, then that drove you insane, and this was meant to be the cause of insanity. So this was the first theory of two branes, TWO, BRAINS. Because nowadays, we're hoping to construct a theory of two branes, very much based on the theory of duality. So, heterotic M theory type models. Well, a typical setup is like this. You have two boundaries, which can be thought of as orbital fixed points, and the theory has a bunch of 5 branes and 2 branes. Those are the only branes we need to think about in heterotic M theory. As far as this talk goes, by heterotic M theory, I'm also going to mean just supergravity on a manifold with boundaries and with some 2 branes and 5 branes thrown in. So for example, the archetypal case would be supergravity on R10 cross S1 over Z2, S1 over Z2 being an interval, so this is supergravity in 11 dimensions with 2 10-dimensional boundaries and various reductions of that. And there's E8 matter on these boundaries. Now, the original motivation for looking at these theories was the idea that, the weakly coupled string, the low energy limit of the weakly coupled string looks like a theory like this when reduced on a small S1. And the idea was that if you made the S1 radius large, it's like going to the large coupling limit of the heterotic string. But this, of course, is just pure conjecture. We'll just study the theory as a low energy, as a quantum field theory, a supersymmetric quantum field theory. Because it would be nice to have some formulation which would derive heterotic M theory as a low energy limit of something. So as far as the M theory map goes, where are we? Well, they're the various string theory and supergravity limits. And I like to think of heterotic M theory sort of limits living along the top edge here between 11-dimensional supergravity and the E8 cross E8 heterotic string. So that towards one end it goes to the weakly coupled string, at least a low energy limit of the weakly coupled string. And the other end it goes to 11-dimensional supergravity. This is very much like what happens with the n-dimensional supergravity limit of the 2A string. Now, these theories are very much used to try to construct superstring phenomenology. So you have to reduce the theory down to 4 dimensions. Typically, you'll do that first by reducing to 5 dimensions. You throw in a bunch of gauge fluxes on the internal space to break the 8 symmetry and fix some of the Clavier moduli. 5 branes typically needed then to get vanishing anomalies. And 2 branes help in some of the moduli stabilization. Anti-5 branes are added to try and uplift the vacuum. I think a feature of heterotic M theory is that very few people seem to be working on it. these collection of 4 people here are a subset of that selection tend to write papers together, and they seem to they have a major part of a major fraction of the number of people working on heterotic M theory, and these people like Laura Anderson, James Gray, and so on, they tend to look at the phenomenology of the theory. But I'm going to look more at the simplest possible theory. I'm going to throw out the 5 branes and the 2 branes, and just concentrate it on the boundary effects. So the idea is you can try and combine what I'm saying today with this work on gauge fluxes and so on to produce a phenomenological theory. I should also say that I'm a cosmologist. I got into this work because James Gray was my postdoc at one time, and I was interested in brane cosmology. I'm not a superstring theorist, so please excuse some of the naivety of my comments today. I'll start off with a sort of a prologue, if you like. Let's just think some of the basics. Think of some of the basics. We have supergravity with boundaries. So let's imagine we have 11-dimensional space and a 10-dimensional boundary, and let's boundary be kind of general. It's curved. It's got matter on it, and has some normal direction, capital N. What we'd like to do in this case is impose a boundary condition on the 11-dimensional gravitino, and the natural one to use is a chirality condition. Gamma 11 times psi is psi. And this makes sense because you'd like the 10-dimensional reduction of this theory to be chiral. So for good sense to go for gamma 11 phi psi in the boundary. It fixes half of the fermion component, seems to make sense. However, there's a major obstacle to this, and that's that the chirality condition is not preserved by supersymmetry, by local supersymmetry. So let's consider a symmetric transformation where we just transform the spin 3 Higgs field by a derivative of a supersymmetry parameter, which is also a chiral on the boundary. And then if we vary this boundary condition, we get gamma NDA from the variation of psi, and also we can rewrite psi as and when we vary psi, we can write that as d eta, write d eta as gamma n eta. So we can write the variation of supersymmetry, of our boundary condition as gamma n dA minus dA gamma n phi non eta. Now the thing is that, if any relativist knows, the tangential derivatives and the normal vectors don't commute, and the extent to which they don't commute is described by the extrinsic curvature. So this boundary condition fails to be supersymmetric whenever we have an extrinsic curvature to this boundary. And this is the case with, as we'll see with heterotic M theory. So heterotic M theory does not have a supersymmetric boundary condition which looks like takes this obvious form. It takes a rather more complicated form. We can look at the boundary condition from another point of view. Let's try integrating the Rita-Schring equation through a surface on which there's matter. And let's also impose a Z2 symmetry around that surface, like we're going to have in heterotic M theory, or like we would need just to get a boundary condition instead of a junction condition. So if we integrate the Rita-Schring equation across a boundary, let's imagine that on one side of the boundary, I've got chalk here. There we go. Okay, so let's suppose, let's put one part of this boundary plus and one part of the boundary minus, so here's the boundary. So the Rita-Schring field on one side of the boundary, we'll imagine, is a reflection of the Rita-Schring field on the other side of the boundary. And we have to realize that with some kind of spinor matrix, which turns out has to be the normal gamma 11. If we combine this reflection symmetry on the spinor with the Rita-Schring equation where there's a source on the surface, let's call it JA. Now if we integrate the Rita-Schring equation through the boundary, we find that we get this equation here which tells us that the chiral part of psi is related to the surface source that we have on the boundary. Now if we realize this source by writing down a surface Lagrangian, then this source will be nothing other than the variation of the surface Lagrangian with respect to the spin 3 Higgs field on the boundary. And again, this is going to be the case in heterotic M theory. We'll find that we'll have a surface Lagrangian which depends on the spin 3 Higgs field and the matter fields, and this will generate a source term which will modify our boundary conditions. So roughly speaking, this is going to be a modified boundary condition. Instead of gamma 11 psi equals psi, we'll have gamma 11 psi equals psi plus this extra term, which depends on the matter fields on the boundary. So here is the application to heterotic M theory. So here's the surface Lagrangian for heterotic M theory. The surface Lagrangian is made out of these this E8 Yang-Mills supermultiplets, and the surface Lagrangian is just given by the F squared term, the kinetic term for the gravitino, and then this coupling between the spin 3 halves and the supercurrent of the Yang-Mills multiplets. And this turns out to be the boundary term for heterotic M theory. There's an extra term in Harava and Witten's paper, but that turns out not to be necessary when you take these boundaries seriously. I just want to point out the coupling in front here. I could have written the coupling in front as 1 on the Yang-Mills coupling strength squared, but I've chosen to write it as some parameter divided by the 11-dimensional Planck scale squared. And this just turns out to be convenient. We'll see later that epsilon will turn out to be something times kappa to the 2/3, so it will itself be related to the gravitational coupling. So a few more things about this. There are these stars hide some extra spin 3 halves extra gravitino terms. The F has some psi bar psi type terms included, as does the connection appearing in the gravitino derivative. Very important on the next slide when we try to find the boundary conditions. We can obtain boundary conditions by varying the full action of supergravity plus this boundary term. And then we get boundary conditions for the spin 3 halves, boundary conditions for the graviton, and to that we have to add, as an extra, boundary conditions on the other field in the supergravity, which is the 3-index antisymmetric tensor field. So I'm going to write this in the supergravity fields as Gij psi and Cijk. Okay, so these are this preliminary set of boundary conditions, some of which you derive from that action. And these boundary conditions have this remarkable property that they are completely supersymmetric. The ones I've written there are totally supersymmetric in the sense that if you do a supersymmetry transformation using the usual supersymmetry transformation rules for the supergravity and gravitino multiplet, well, with some supercovariantization and some of the terms, you find that these boundary conditions are completely supersymmetric. Now, in regional work of Harava and Witten, they expanded everything in powers of this parameter epsilon. However, this statement about supersymmetry applies to all powers of this epsilon. These are completely supersymmetric boundary conditions, in the sense that if I transform this set of boundary conditions, the transformation is 0 if I impose the boundary conditions. You see what I mean? This set varies into itself. Interestingly, you notice the sources on the right here are the supercurrent of the Yang-Mills supermultiplet and the stress energy tensor of the Yang-Mills supermultiplet. Remember, K here is extrinsic curvature. And the middle condition there it gives a boundary condition on the 3-index antisymmetric, or the tangential components of the antisymmetric tensor field from supergravity. The gravitino boundary condition has this odd term involving epsilon gamma, which you see here. Now you can see this arising in two ways. One way it arises from varying, from variation of the gravity of the gaugino kinetic term with respect to the spin 3 halves fields that appears in the connection here. Another way of looking at it is that if you try to construct a supersymmetric set of boundary conditions, you find that you have to include this term here in order to get supersymmetry. You don't get supersymmetry if you don't include this term here. This term will be important for what I'm going to say later about getting a vanishing cosmological constant with moduli stabilization in heterotic M theory. Now these boundary conditions, I said, they're exact. They're exactly supersymmetric to all orders than epsilon. However, there is a caveat here, and that's that these are missing a term. In just a moment, we'll look at anomaly cancellation. And when we look at anomaly cancellation, we'll see that there is this term is not enough, and we have to add a Lorentz-Chern-Simons term. By this is a Yang-Mills-Chern-Simons term. You have to add a Lorentz-Chern-Simons term to the boundary condition for C. And when we do that, we have to start adding curvature and higher derivative terms to these here. And then, so far, it's only been possible to construct supersymmetric sets of boundary conditions up to a given order and curvature. So you have to do expansion in powers of curvature here. So this exact supersymmetry, unfortunately, no longer applies. It's exact to all orders of epsilon, but it only applies up to whatever order you feel strong enough to pursue the expansion in powers of curvature here. And it'd be nice to try and find some kind of superfield formalism of all these boundary conditions. Maybe it's possible to find a set of boundary conditions which is completely supersymmetric, even when you include the higher order derivative terms. Okay, so that basically is that's the theory. The boundary conditions are supersymmetric. Also, the Lagrangian is fully supersymmetric to all orders in epsilon, modulo having to add these extra R squared terms. So let's have a look at an application of this to anomaly cancellation. And I want to bring out here is that boundary conditions rather than Bianchi identities play an important role, because you're all familiar with the fact that when you have branes, you have this anomaly in flow, and this has to do with modifications to the Bianchi identity, distributional terms and Bianchi identities, and so on. When we take these boundaries seriously, we don't need to modify the Bianchi identities. Instead, the role of that modification of the Bianchi identities is played instead by boundary conditions. In fact, there's a lot of problems with the original formulation of heterotic M theory, which came about because Harava and Witten were trying to modify the Bianchi identities because they knew you have to do that in 10 dimensions. They thought we should do that in 11 dimensions, and then it will reduce to the modification of Bianchi identities in 10 dimensions. But in fact, modifying the Bianchi identity in 11 dimensions gives you all sorts of problems, because that means basically making the 3-index field have a distributional correction. But the trouble is then that the G flux has a distributional correction, and when you plug that back into the supersymmetry transformations, you've got distributions in the supersymmetry transformations, and when you apply those on the boundary, you end up getting squares of delta functions, and a rather badly behaved theory. So we avoid at all times, we avoid modifying the Bianchi identity in 11 dimensions. However, when the theory is reduced, we get a modified Bianchi identity in 10 dimensions. It just comes about from reduction. Let's look at the anomaly. So if we just take no 5 branes, the anomaly is just going to be the contribution to the anomaly just comes from the dimensional gravitino and 10-dimensional gaugino. And the familiar story is that this produces an anomaly which descends from a polynomial which factorizes, and there are basically 2 terms. I just had to wake up. So there are basically 2 terms. The anomaly, the first term in the anomaly is going to be cancelled by variations of the CGG term, where G is the flux of the C. The CGG term, the supergravity action, and the second term in the anomaly is going to be cancelled by a CX8 term in the supergravity Lagrangian. I'm going to look at these 2 terms in turn, although this may seem like a familiar or at least a very old piece of work. Actually, there are some interesting modifications to this when we take the boundaries seriously, and the interesting modifications to both of these terms in the anomaly. So first of all, let's see how we're going to fix up, how we're going to do anomaly cancellation using boundary conditions rather than modification of the Bianchi identity. So far we had a boundary condition which is basically epsilon times the times the Yang-Mills-Chern-Simons term, but we're now going to add the Lorentz-Chern-Simons term to that boundary condition, and I'm going to drop all the fermion terms that were in that boundary condition. So if we take the exterior derivative of this, then the boundary condition on the flux, on the field strength of C is going to be epsilon I4, where I4 was that term in the anomaly. So this is how it goes. So under gauge transformation, the right-hand side of the boundary condition transforms by an exterior derivative involving the gauge parameter. So we can fix this up by doing an abelian gauge transformation of the of the 3-index antisymmetric tensor field. So this is nice because in the normally inflow picture, you have to start modifying the definition of the flux to get the field strength to get a conserved field strength. Now all we're doing is an abelian transformation, which certainly will preserve the field strength. So we pick any 2 form which is fixed on the boundary to have the value that we want with trace alpha f. Okay, so any 2 form which has the value trace alpha f on the boundary. Then when we put this abelian transformation into the bulk part of the action, the CGG term picks up a boundary term under this variation, which is precisely this trace alpha f times the GG, which is precisely going to cancel the anomaly from the I43 term. Now the boundary condition has this factor epsilon. The G has an epsilon, so we've got epsilon cubed. This term also has a 1 on kappa squared, and the anomaly basically has a 1 in front of it. So we get epsilon cubed over kappa squared. So we've got epsilon cubed over kappa squared is something like 1. So we get epsilon comes out to be a number times kappa to the 2/3. So that's the consequence of anomaly cancellation. Not a new result, but well, I say not a new result. Actually, the numerical factors seem to be different if we use this boundary picture than if we use the so-called upstairs formulation of orbifolds. A couple of interesting things. The theory, the action is constructed very much by relying on supersymmetry and anomalies. But when you do that, you find you can't just make a supersymmetric action because of supersymmetric anomaly. So the supersymmetric anomaly here actually comes in, plays an important role when you're constructing the action, because you have to remember you don't make the action supersymmetric, you actually make it supersymmetric up to the SUSY anomaly. It's kind of interesting application of the supersymmetric anomaly. Also, there are fermion terms in this boundary condition. So when we do this cancellation of the anomaly, the fermion terms are going to come in, but there are no fermion terms in the anomaly. So what we have to do is add extra Green-Schwarz terms involving fermions to the theory when we do this anomaly cancellation.
So can I ask a midnight question?
Yeah.
Here what symmetry do you discuss?
So what? So this is the Yang-Mills symmetry, E8 Yang-Mills symmetry on the boundary. There's also the Lorentz symmetry, but that goes through in exactly the same way.
So the anomaly of the gauge symmetry and the local Lorentz?
So did gauge?
Gauge symmetry and the local Lorentz symmetry you are discussing?
Yeah, so I'm just, here I've just done a gauge transformation, but I can do exactly the same. There's a -1/2 d of trace of the Lorentz, the infinitesimal Lorentz generator times r as well. So I've, just to simplify things, I've set the local Lorentz generator to be 0, but it all works out just the same. So that's right, so it's a Yang-Mills symmetry and local Lorentz symmetry. Actually, there is an interesting thing that when we do the local Lorentz symmetry, we usually just transform, because the anomaly just depends on, because the anomaly lives on the boundary, we always just consider Lorentz transformations of the boundary. That is, in a sense, we keep the normal direction fixed here. So it's local 10-dimensional Lorentz symmetry and the E8 Yang-Mills symmetry. Now there are 2 boundaries, and I just talk about one boundary, but each boundary is has a similar E8 symmetry. E8 gauge symmetry. And this is the abelian symmetry of supergravity in 11 dimensions.
This other approach that you're alluding to, which gives you a different factor, how do you reconcile these two?
Well, this other approach that gives a different factor has to really deal with... The problem is, in the other approach, you always get products of distributions with things that you don't want to multiply distributions by. So the theory is full of distributional squared terms. In this anomaly cancellation, the problem is a product of distributions and theta function, Heaviside functions. And it's a question really of how you interpret those products of distributions and Heaviside functions. So you can get different numbers here depending on how you interpret a product of a distribution and Heaviside.
So it's regularization.
So basically it's a regularization of that product. And people had decided, I think most people had decided that they knew the best way to regularize that product. But that gives a different answer than this boundary condition does. It's a factor of 2. So there are complications in the orbifold picture which make the result slightly unclear. Whereas in this boundary picture, it's absolutely rigid. There's no doubt what that coefficient is.
So in a sense, you would claim that this allows you to fix the regularization of the original concept.
That's the way I would claim it. Since we don't have anybody in this room who's working on the alternative picture, it's a bit unfair to criticise. Yeah. I was Kelly Stella grumbled to me when I did this at first. Kelly Stella complained that just everybody thought they'd sorted this out. I'd managed to muddy the waters again. Let's have a look at the I4X8 term, because I think this is where the most changes occur. The main thing here is that the X8, remember that was the X8 was this trace of R4 minus trace R squared. The thing about the anomaly is it depends on the surface, on the curvature of the surface geometry. If we write omega d for the surface connection, X8 depends on the curvature of the surface connection. It's completely property of the boundary. By the way, I produced a preprint recently with a proof of that result. Although there is an older proof by Dan Freed, which is quite hard. This is quite simple, I think. Now, when we write down a term in the bulk that's going to cancel this anomaly, we've of course got to use the 11-dimensional curvature. And something that's always worried me is how do you cancel 11-dimensional curvatures with 10-dimensional curvatures? Well, first of all, we know that there is a term like CY8 because you need that term to cancel anomalies from the 5 branes. So let's try putting that term in. Now, a crucial observation here is that the difference between the Y8 for the 11-dimensional curvature and Y8 for the surface curvature can be written as an exterior derivative of something involving extrinsic curvature. And you know this must be true because Y8 and X8 are both characteristic polynomials, so you know that they are both d of something. So because the difference is d of something. The important thing is that something just depends on the extrinsic curvature. So let's consider this new Green-Schwarz term, which has this 7 form in it, and the Chern-Simons, the Yang-Mills and Lorentz Chern-Simons terms in it. So what happens then? Let's consider what happens when we vary this second term here. If we vary and this thing again, just consider the gauge transformation to start off with. If we vary the Lorentz Chern-Simons term, we're going to get a trace alpha f, d of trace alpha f, and when we integrate that by parts, that will give us a trace alpha f times dx7. Now that is going to cancel the term we get which from the Y8. I'm sorry, we were running a bit late, so I didn't have a chance to. So that's going to cancel the term we have when we substitute this Y8 in here, and we have a d chi7 here, and then we do the abelian transformation on the C. So this term is going to precisely cancel this d chi7 term. So this is a term that depends on extrinsic curvature here, and there's a boundary term, a boundary Green-Schwarz term, which is going to help cancel this part of the anomaly. So when you do this variation, the gauge variation of this term plus this term is going to give us a term which will precisely cancel the anomaly. Now I think this is an opportunity perhaps to try and test this boundary formulation of heterotic M theory. Because if we now reduce this, remember the boundary condition, let's see, here we go. The boundary condition on the extrinsic curvature depends on the stress tensor of the matter multiplet. So in particular, it depends on things like f squared of the Yang-Mills field. So if you put that in to chi7 here, we'll have things. This will have things depending on Yang-Mills fields. So this term, when we reduce to 10 dimensions, is just going to be a bunch of Yang-Mills fields, and then when we reduce this it's a bunch of curvature terms. So we can actually try and see if because when we reduce to 10 dimension, we're supposed to get a low-energy limited heterotic string. So we can see whether we can reproduce these terms in the effective string Lagrangian heterotic string, maybe by calculating string scattering amplitudes. So they're suggesting here that there are new terms from the boundary which might be seen in the low energy effective limit of the heterotic string. I click my superstring amplitude. And if that was the case, then it would sort of confirm that this boundary approach is a thing to do. Because it could be. The original formulation of heterotic M theory by Harava and Witten had these horrible delta function squared terms in it. It's very badly behaved. And at the time, the reasoning was that since this is connected to a string theory, maybe we expect sort of point-wise things to be badly behaved. So maybe this is just a sign that really the low energy limit of this theory is badly behaved. Now it could be that the original formulation of Harava and Witten is correct. It just is a badly behaved theory, a badly behaved field theory. On the other hand, here's a nicely behaved field theory, which also claiming to be the low energy limit of the heterotic string. So the question is, which one is right? So then it becomes a question of finding things which you could compare, for example, with superstring calculations. And this is what I'm suggesting here, that this sort of boundary term, this boundary Green-Schwarz term, which only arises in this sort of boundary formulation, might have some effect in the 10-dimensional heterotic string Lagrangian. I should also own up to the fact that this is very much incomplete work. It only worked, say, a few days ago. And it's not complete yet because there's a problem here that this term here, it seems this term here is not invariant under local Lorentz symmetries on the boundaries. That it doesn't just depend on extrinsic curvatures. There seems to be some connection terms in there as well. And that really messes up this cancellation here. So the suggestion here is that there are extra Green-Schwarz terms needed to fix up the anomaly in the Lorentz symmetry of the boundary. So there's an unresolved problem. It'd be interesting to sort that one out. If anyone has any ideas, it'd be interesting to hear. One thing, going to some of the other talks here, one impression I get is it is a much simpler theory to work on than many of the things that people are doing in D-branes these days. Because so few people are working in this area, there are many sort of basic problems that have not been addressed yet. And it's really nice to work in an area where it's still fresh in a way, even though it's not particularly young. I could say something about the fact that when we include these Lorentz-Chern-Simons terms, the boundary conditions are modified then by R-squared terms, and so is the Lagrangian. You construct these R-squared terms in a similar way you would do constructing R-squared terms in the low energy limit of a heterotic string or type 2A string. And there's this nice trick where you try to treat the graviton and the derivatives of the gravitino as a sort of pseudo Yang-Mills multiplet and build up curvature terms that way. And when you do that, you find you have to include G-flux terms, that is the exterior derivative of the three-form field strength. You have to include G-flux terms in the definition of the connections. But that means, because the Lagrangian and the boundary conditions, the supersymmetry are so tightly bound together, that you find that there must be G-flux terms in the anomaly. And as far as I know, maybe someone can correct me, no one has successfully worked out G-flux terms in anomalies. In this case, no one's worked out the G-flux terms that you would get in the anomaly for 11-dimensional supergravity on a boundary. There's been an attempt by Greg Moore, but I think the work they did is what's unpublished, and I think is not correct. So there's an interesting issue, just a basic issue in calculating anomalies with G-flux terms. By the way, because the supersymmetry, the boundary conditions, and the Lagrangian are so closely tied together, you can get a lot of information, perhaps even the complete formula for the anomaly, just from looking at supersymmetry of the boundary conditions. So it's interesting, you can get something for free. That is, if anomaly cancellation does happen, then that tells you something about the form of that anomaly. Interesting to work further on that as well. So that's all I've got to say on anomalies. Any questions on anomalies? Perhaps make them know. So that gives me 20 minutes for moduli stabilization. So if we don't have 5 branes, then we're sort of restricted to considering E8 cross E6 Calabi-Yau reduction, where a gauge flux, a Yang-Mills gauge flux, will reduce one of the E8s down to E6. If we take the simplest Calabi-Yau spaces, then the moduli are basically just going to be the volumes of the Calabi-Yau spaces on the two boundaries. Because we have all sorts of shape and complex structure moduli for the Calabi-Yau spaces, but let's forget about those. Maybe it's just a simple Calabi-Yau space. Just focus on the moduli, which is the volume of the Calabi-Yau space. And because we've got an 11-dimensional theory, we'll reduce with a Calabi-Yau space. We'll reduce to 5 dimensions, and the background solution will depend on just two moduli, which turn out that you can choose to be the volumes of the Calabi-Yau spaces on the two boundaries. You could pick the Calabi-Yau volume on one boundary and the separation of the two boundaries. That's equally valid choice. It turns out that the volumes of the Calabi-Yau spaces are better, and you can see that if you look at the Kähler potential of these moduli in 4 dimensions, and it actually takes a simple form when written in terms of these the superfields which have these volumes as their leading order components. Whereas if you try to write the Kähler potential in terms of the separation modulus and just the volume of one Calabi-Yau space, it's a real mess. Now there is one simplification. If the brane separation is small, and we're interested in small brane separation, but not necessarily the weakly coupled heterotic string limit. It's possible to have small brane separation compared to other parameters and still be in the large limit, large coupling limit. If we take the small separation limit, then one of the volumes basically becomes an average volume of the Calabi-Yau space plus something times the separation modulus, and the other one is like an average volume minus the separation modulus. By the way, and these are S and T. I've used S and T because these names people use these for these fields in string theory. This, by the way, is first introduction to this parameter alpha, which is going to make an appearance quite a lot. For example, if we have a Yang-Mills background that induces a background G-flux, and that background G-flux is this parameter alpha times a 2,2 form on the Calabi-Yau space. Alpha is also related to the strength of the Yang-Mills background. And you can relate alpha to, for example, the Pontryagin number of the Yang-Mills field and various other constants. So basically, alpha is telling us about the size of the G-flux or the size of the Yang-Mills background. I hesitate to use that word, but it's sometimes called the brane charge, but I stress this is a boundary, not a brane. If we generalize this a bit, typically what you'll have is internal Yang-Mills fluxes fixing various Calabi-Yau moduli, complex moduli and 1,1 moduli. Gaugino condensation helps fixing Calabi-Yau volume moduli. And then you've got this extra modulus, which is like the separation of the two branes. And one way of trying to fix that is to have two branes stretching between the two boundaries. And if you combine these various tricks, you can get reduction with stable moduli and sort of reasonable phenomenology. But I say I'm just going to talk of a case which has rather bad phenomenology, just E8 cross E6, where in a trivial Calabi-Yau space we only have to worry about the volume modulus. When you do these tricks for fixing the moduli, typically you will want to retain some supersymmetry, and that will lead to a negative cosmological constant. Now, because there's so much work done on type 2b phenomenology, and partially that's because there's a natural uplifting mechanism there from the KKLT mechanism. If you throw in an anti-D brane into type 2b string theory, you can get these moduli stabilizations with vanishing cosmological constant. And of course, part of that picture is that you look among the lots of different compactifications with lots of different internal fluxes and find the one that just has exactly the right negative potential, which will then cancel off the positive contribution to potential from the D branes, anti-D branes. Now what I'm going to do now is sort of present a mechanism in heterotic M theory for uplift. So the idea is that we stabilize the moduli using these kind of tricks here, and that leaves us with a negative cosmodular constant, and then we uplift using, well, just an effect of the boundaries. So I have to say a little bit about Gaugino condensation before I can say, because Gaugino condensation is going to play a role here. The Gauginos, which live on the 10-dimensional boundaries, they can condense so that these bilinears are then related to the moduli, the volumes of the Calabi-Yau spaces on each of the boundary, and then these condensates then have an influence on the theory because these condensates appear in the boundary conditions. So the boundary conditions, there was all this stuff involving the Chern-Simons terms, but then there was also stuff involving these fermion bilinears. So now, when we do Gaugino condensation, it's these fermion bilinears that are going to play an important role. So what they do is induce some background C, some background 3-index antisymmetric tensor field, and that will then give you a potential. And you can work out the superpotential corresponding to that potential. And it takes a very simple form. It's just basically the condensate, the thing that appears as a condensation of the Gaugino bilinear, times a bunch of parameters. There was this alpha, which sort of gives the strength of our background solution. And this parameter epsilon, which is the thing that appeared in the Yang-Mills action, which is basically capital 2/3. It's interesting that if you use the boundary formulation, you get a very simple superpotential. If you use the old orbifold formulation, you get corrections to this superpotential involving V1 and V2, and you get a much more ugly expression, which sort of just shows how much nicer the boundary formulation is. It doesn't mean it's right, it just tends to give you nicer results. Okay, so we can use this superpotential, then maybe add something that we imagine comes from these internal fluxes, and but let's imagine all that sorts itself out and just gives us a constant term in the superpotential, and try to do a moduli stabilization. So here's an example. If you imagine you had two Gaugino condensates, not very physical, but imagine we had two Gaugino condensates, one on each boundary, then we'd have a superpotential like this, and that gives a potential which is plotted here. So V1 and V2 are the two volumes of Calabi-Yau spaces, and this potential has it has a minimum here, but it's negative. It has a saddle point, and it goes off to 0 out here as well. So the uplifting comes from Casimir energy, comes from quantum vacuum energy. And the reason that we get a Casimir energy is because of the fermion boundary condition. So let's throw away all the stuff on the right-hand side of the fermion boundary condition. Let's concentrate just on the first two terms in the fermion boundary conditions. Remember, P plus is just a chirality operation. So this is just the plus chirality part of the gravitino. And then we get this strange term here, which sort of twists in some of the left chirality part of the gravitino times this 2 fermion term. Now, this term happens to be, it happens to involve precisely the same Gaugino bilinear that appears in the condensate. So we have a condensate. This twist here, I can think of it as a kind of chiral twist in the gravitino, is the condensate times epsilon here. So if there's no condensate, we just have a simple chirality condition if there's no, to put the boundary fields to 0. But if there's a condensate, then we get this sort of strange mixture between the sort of left-handed and right-handed gravitino components. Now you might ask, can we sort of gauge this away in some way? Well, chirality is not gauged. You could try a global transformation if this is constant, but then if the condensates on the two boundaries are different, then you can't transform them both away by sort of global chiral rotation. You can transform one away, but then you've got one left on the other boundary. So if you have any condensates and the difference on the two boundaries, for example, 0 on one boundary and non-zero on the other, then we really have a non-trivial twist between the fermions on one boundary and the gravitinos on the other boundary. Actually, it's interesting, if you go back to 1995 or so, Harava considered what would happen if you have opposite chiralities of the gravitinos on the two boundaries of heterotic M theory. And in fact, I think some people considered this as a possible mechanism for supersymmetry breaking, and people calculated vacuum energies in that context. In that context, what people did was always to give the gravitino one chirality on one boundary and the opposite chirality on the other boundary. That is the thing you're not supposed to do for heterotic M theory. What's happening here is that you don't get such a drastic twist, you get just a slight twist in chirality between one boundary and the other. However, these boundary conditions were supersymmetric if we're allowed to vary the gaugino, but as soon as we fix this term, this is no longer supersymmetric, so we're breaking 5D supersymmetry here. And because of that, we get a non-zero vacuum energy. It's easy to calculate the vacuum energy, because if we assume the vacuum energy is zero in the supersymmetric situation, then we just calculate the difference between the vacuum energy with this twist and the vacuum energy without this twist. And the only field that comes in here is a gravitino. So you just have to calculate the gravitino vacuum energy. It's quite straightforward. So what do you get? Well, first of all, let's imagine we reduce to 5 dimensions first, and we'll ignore the contribution from the modes on the Calabi-Yau space, just consider the contributions from the 5th dimension. So let's suppose the size of the extra dimension is L5, and the magnitude of the condensate is C. So we have some picture that's sort of, so we have a brane here and a brane here, and the separation is L5. So a boundary here and a boundary here, and the separation is L5. So Casimir effect in 5 dimensions typically will give you a potential that goes like L5 to the minus 4. Here though, there's a bit of subtlety, because you have to, we want to transform everything to the Einstein frame, whereas you do the Casimir calculation in the 5-dimensional frame, and there's a contribution from transforming from the 5D Einstein frame to the 4D Einstein frame. This gives this awkward little factor of L5 minus 2 here. And then we get this epsilon kappa to the 2/3 squared, and then this condensate scale squared. So if this is just epsilon c that appeared in the that appeared here, epsilon times c. So that's the sort of quantum contribution to the potential due to this supersymmetry breaking. Now the condensate has a negative potential. Let's see what it was. So at the minimum of the potential, the potential is going to look something like W squared, which is C alpha epsilon squared. So there we go, C alpha epsilon squared. There's a kappa 4 minus 2 in front of that, just the definition of the potential. And then you find there's this alpha L5 minus 1 just comes out in the wash, as it were. Now the idea is you consider lots of different reductions, and one of them might just have the right value of L5 such that these two terms cancel and give you a vanishing cosmological constant. Now if that's going to happen, L5 will end up having this value here, alpha minus 3 halves kappa 4 to 2/5. Now I've not said much about the phenomenology of these models, but you can relate the value of alpha to the fine structure constant and the 4-dimensional Planck length by this formula here. And if you put that into the L5, we get something like alpha gut to the minus 9/10 times the Planck length, which is good because it's substantially larger than the Planck length. Oops. So we seem to be consistent here. That is, if we can find a reduction that has this value of L5, it will be consistent in the sense that the separation of the branes will really be bigger than the Planck length. There is, unfortunately, one feature of this that's not quite consistent, and that's that the calculation was done assuming that the Calabi-Yau modes decouple, which is basically saying that the Calabi-Yau space is smaller than the separation L5. Unfortunately, if you work out the size of the Calabi-Yau space in this case, it turns out to be the same as L5. So either, well, try to modify the model to find a case where L5 is bigger than the Calabi-Yau space, or calculate the contribution of the Calabi-Yau modes. Or another possibility is that you could choose a Calabi-Yau space which has, just by chance, very large eigenvalues. And therefore the sort of masses of the Calabi-Yau modes will be large simply because the eigenvalues on Calabi-Yau space are larger than they ought to be, because the Calabi-Yau space has quite a complicated topology, for example. So it might be possible to decouple the Calabi-Yau modes just by having a complicated Calabi-Yau space. That raises an interesting question about what is the size of the first eigenvalue on a Calabi-Yau space, and can you make it as large as you like by making the Calabi-Yau space have a complicated topology? Leave that to mathematicians though. So the bottom line though is the twist in the fermion boundary condition has broken 5D supersymmetry and led to the Casimir force between the branes. And here is the well, this looks the same as the other picture. So basically all that's happened is that now the minimum here is at zero cosmological constant. So we have a potential which has a minimum at zero cosmological constant. It has a nice saddle point. It's the kind of potential you might start thinking about doing inflation with as a cosmologist. It was my original motivation for looking at this problem. It turns out the potential here is a little bit steep, but then again that's what happened with KKLT. The potential was rather too steep to do inflation, and a similar thing seems to happen here. But then again, this is the simplest model, and so far is not including, for example, 5 branes, and it's just an E8 cross E6 reduction. Well, that sort of basically gets to the end of it. So what I've tried to present is the idea that heterotic M theory can be defined on a manifold with boundary. And what you get is a theory which is completely supersymmetric and anomaly free, although, as I said, there's still some things remain to be done even in that very basic problem. And there are no modifications of the Bianchi identity for C. So that is sort of perhaps the crux of the difference between what I'm presenting here and what people normally do with heterotic M theory. The G is DC, everything is completely bona fide, and everything is done through boundary conditions rather than modifying Bianchi identity. There are new Green-Schwarz terms, which I think are new and sort of incomplete at the moment, and it'd be interesting to see if those Green-Schwarz terms show up in, for example, in heterotic string theory. And I try to suggest there's a natural uplifting mechanism in this theory. I think it's a very simple toy model. What I've not done is, well, I've said nothing about the other moduli, and fixing those other moduli is really where most people are at in heterotic M theory these days. We're going to have to try and combine that with some of these ideas. And also, I've said nothing about 5 branes. Putting 5 branes, the amount of sort of anomaly cancellation you need to do on the boundary then is changed. So you might want to start modifying this term here. But the supersymmetry then is sort of very rigid. There's very little you can do to modify those boundary conditions I gave. So there's a whole lot of stuff needs to be done to try and include 5 branes in this picture. So this is very much a field that's, despite being 17 years old, it's really a field that's still in very early stages of development yet. Okay, that's all I have to.
Do we have some time for questions? Okay, well, if there are no questions, then let's thank Ian again.